everyone. So in this video I want to talk about the connection between what we've done so far, which has been a lot to do with limits, and then a little bit of an introduction into the definition of the derivative and what that means for what we're learning moving forward in this new chapter. Okay, so first what I have here is the definition of the derivative. So the definition of a derivative has a limit in there. The derivative is a huge part of calculus. And so if you want to sum it up in terms of what we do for our class, I mean, really we did a lot to cover limits, and it was just so that we could get to this definition of a derivative. It's so we could understand what a limit is and then apply that understanding to this definition here. So this definition is really important. I've got kind of a diagram over here on the right. So let's say if you just take one point, and here I just called it x and f of x. So basically if I have a value x, which could be anything, the y value we could write as f of x. And then let's say you take another point, and instead of just defining an entirely new point, we define it in terms of the first point. So x plus h actually means you start at x, but then you increase. H could be negative, so you could decrease as well, but that's basically saying how far you go away from that original point. That's going to be your new x value. And then if you plug x plus h into the function, that's going to be your new y value. And I'm going to write something here, and then I'm just going to erase it, but the slope equation is y2 minus y1 over x2 minus x1. The average rate of change formula is one way to look at it, f of b minus f of a over b minus a. I mean, these are using different notation, but basically they're the exact same thing. The wording is different because when we talk about the word slope, specifically we're talking about a linear equation. And that's because with a linear equation, no matter what point we choose on the graph, the slope's going to be the same no matter what. It doesn't change. As opposed to average rate of change, we talk about for non-linear functions. So if we have something like this, like let's say a parabola, at different points on the graph, the actual slope, like if we drew a line through it to kind of show what that slope looks like, would be different based on which point we chose on the graph. Okay, let me erase this. How does that have to do with this definition of a derivative? Well, this part here, which is actually called the difference quotient, is the same thing as average rate of change. It's one of those things where it looks different, but it means the exact same thing. And the way that I could write that out is to say, instead of a being our starting point, we're calling that x, and instead of b being the second point, we're just defining that to be in terms of the first point. So instead of just doing a separate point b, we're saying start at x and then increase or decrease by this other value to get another point. And then if you plug it into that slope average rate of change formula, that becomes f of x plus h minus f of x all over the first x value, which is x plus h, minus the second x value, which is x. And then what happens here is that the x minus x cancels, which leaves that difference quotient. So essentially that average rate of change and difference quotient formulas you can use interchangeably. Okay, so that's the slope part of this. The limit part, now what we're trying to say is that we want to know, when we're looking at the derivative, we don't want to know what the value is at that point. Let's say if we think about an example that has to do with profit. We might have a profit function. Let's say this blue graph that I have is indicating profit. We can choose any ordered pair on there, and we could just figure out, okay, this is the profit when you sell this many units, this is the profit when you sell that many units. When we look at the derivative, we're not looking at that value, we're looking at how the value is changing. So is profit increasing which would be going in an upwards direction, or is it decreasing, which means if we're selling more, would we expect, how much of a change in profit would we expect? Okay, so looking at this visual again, the limit part is basically saying if h goes to 0, that means we want the distance between that first and second point to get smaller and smaller. So those 2 points are going to get closer and closer together. So I want this point to get closer to that one. And first, before I do that, let me draw this line through here. So the average rate of change would basically mean that if you drew a line through both of those, you could use that line as an approximation for the actual slope or the change. But if you get these points to be a little closer, let's say you bring it in here instead, so h is smaller, now when you find the average rate of change, it's a better approximation. And so if we want an even better approximation, we could go a little closer, which would be a smaller h value, and we get the slope, and we're getting closer, and you could get, what we're happening now is like h is so small, like they're kind of like points right on top of each other. And when we say h approaches 0, we're using that idea of a limit, which means it can't actually be 0, because then you can't find the slope or the average rate of change. And, we can't divide by 0 in the denominator. So we're using that idea of limits where we're like, we know it's not 0, but we're just going to keep going to try to get closer and closer and closer to 0 as possible to get the best approximation. And I want to show you a little animation about that. So let me get out of here for a second. Okay, here's an animation. We've got another parabola graph. I'm going to use the sliders here. So here we've got our A value as 2.9, that's the black dot there, and then an H value. And so here, let me make it a little bit farther. I have H as 2.6, so the distance between those 2 points is farther, but then if I make H get smaller and smaller, that point gets closer and closer and closer and closer and closer until they're basically the same point, and then the line between them is what's called the tangent line, which tells us the slope or how it's changing at that single point on the graph. And I'm going to add in now, let me make h bigger again, the actual tangent line right here. So what we're doing with that definition is like we're starting with the red line and we're trying to get to the blue line, and we're doing that by taking smaller and smaller values of h to get to that tangent line. Okay, so I know this is a recap from before, but I think it's important to go over the whys of this just so that going in to when we do all these applications in calculus that you really understand what the derivative is. All right, so let's look at an example. Okay, let's say we have the function f of x is equal to 3x squared plus 7x plus 9, and we want to find the derivative. I'm going to use the definition. Okay, so to plug everything in, you could plug it in pieces. I'm going to try to do it all at once. So f of x plus h means everywhere I see an x, I'm going to substitute in an x plus h. So I've got 3 times x plus h squared plus 7 times x plus h. And whenever I plug it in, I like to put parentheses around it. And then minus f of x, which just means to rewrite the function as it is. But I put parentheses around this whole thing to make sure that I subtract everything all over h. So with limit problems, some limits you can just plug in h is equal to 0 and then get your answer. But this is a case where if we plug in 0, we will actually get 0 in the denominator, and we actually get 0 over 0, and that's what tells us you need to simplify first and then find the limit. So if we were to plug it in, we would get 0 over 0. So to simplify, let's see, there's a couple of things I want to do. First, I might look here, x plus h squared means x plus h times x plus h, so you have to FOIL it out. X squared plus xh plus xh plus h squared. So the xh's are actually like terms, so I can combine those together and say 2xh plus h squared. So then if I plug it back in here, that would be 3 times that whole thing, because I just squared it out. And then I'm just going to rewrite everything that's already here. I don't want to skip too many steps because then it can be hard to follow. And I'm just leaving everything else as it was without making any changes. Don't want to forget I had the limit in front, so I'll keep that. This whole thing is over h. Okay, so now I'll do some distributing, and I realized here that squared shouldn't be there. I'll just do some distributing. So that 3, since it was multiplied, is going to get distributed to those 3 terms. The 7, I'll distribute, and the negative as well, making sure to change all the signs of everything after that. So that gives me 3x squared plus 6xh plus, I see what I had done with my square before. It's h squared. I just had it, for some reason, on the outside of the parentheses. Plus 3h squared plus 7x plus 7h plus 9, and then minus 3x squared. See, I almost forgot to distribute there. Minus 7x minus 9. Okay, so you get this big long piece here. I realize that I haven't put the h in the denominator and I haven't wrote the limit, and I am going to skip that step for right now. And then just instead kind of show all the cancellations that take place. So when you are working these types of problems, there should be a lot of cancellations that take place. Really everything without an h should end up canceling. So let's see, the 3x squared minus 3x squared cancels, plus 7x minus 7x cancels, and then plus 9 minus 9 cancels. And now let me rewrite the problem. Limit of h goes to 0. In the numerator I have 6xh plus 3h squared plus 7h all over h. So now that everything in the numerator has an h in it, I could actually think about factoring that out and then canceling it with the h in the denominator. So I've got now the limit as h goes to 0 of 6x plus 3h plus 7. So now I can go ahead and plug in h is equal to 0. So it's 6x plus 3 times 0 plus 7, which is equal to 6x plus 7. So in this case we have a function as an answer, and this is actually the derivative. So we could say that f prime of x is equal to 6x plus h, and then I'm going to go ahead and write the original function too. So what this means is that now we've found this equation where if we want to find the slope at any point on the original function, we can just plug it into this derivative function. So how is f of x changing at x is equal to 2? Well, then we could plug in 2 into the derivative and it'll tell us how the function is changing at that point, x is equal to 2. Okay, so that's the idea of the derivative. What are we doing now when we move into chapter 4? What we're actually doing is we're learning the shortcuts. So it's like we've done all this work to try and find the limits, to understand the concept. Now we can actually start using the shortcuts. And you might be like, I didn't want to go through all that learning of the limits first. But it is really important to understand the concept first. But on the bright side, it's nice that you don't have to keep using this limit definition over and over and over again, because that would take a lot of work for all the applications that we're going to cover. All right, so let's look again at this function. F of x is equal to 3x squared plus 7x plus 9. Some of the first shortcuts, which we can call the derivative rules, are the power rule is one of them. And so that actually applies to these first two parts. And I'm not going to write all the derivative rules down here, but that is what we're covering. And really all of Chapter 4 is learning all the derivative rules and then applying them in different cases, different problems. And so the power rule is probably the one that gets used the most, which is that if you have something like x to a power, the derivative is actually to bring that down, and then the exponent gets reduced by 1. So if we just looked at x squared, for example, what that means is that the derivative would be 2x, and then now the exponent would become 2 minus 1. And we could simplify that to be 2x. If we have x, which we could rewrite as x to the 1, that means 1x, 1 minus 1, which is 1x to the 0. Anything raised to the 0 is 1, so our answer in this case is just 1. So something to keep in mind with the power rule is that if there is an exponent, it gets reduced by 1, and you have to bring that number in the front. And when you apply that to just a single x, what happens is it looks like that single x just sort of disappears, but it's actually part of that power rule. And then if you have a constant, like what we have right here, it always goes to 0. So looking at the whole thing again, using this recap of the rules that we're going to cover in Chapter 4, if I have f of x is equal to 3x squared plus 7x plus 9, how do we take the derivative? Well, you could use the limit definition, which I've already shown, but now I want to show you how to do it using these shortcuts. So in this case, I notice that there's this x squared and there's a 3 in the front. One of the rules is if there is a coefficient that you can just leave the coefficient there. So it's going to be 3 times whatever the derivative of x squared is, which I've said is 2x to the 1, plus 7 is multiplied by the x, so I can just leave the 7 there and multiply it by the derivative of x, which using the power rule is really just a 1. Plus, and now if we look at 9, but it's by itself, there's no variable attached to it or multiplied to it, that is just going to be 0. So the answer for the derivative is 6x plus 7. Which, if we look back at our work from before, that was exactly what we got using the limit definition. So maybe you could say a benefit of learning the limits first and the limit definition is that you can trust these shortcuts that we're now covering in Chapter 4, because we could go back and do this sort of long work of the definition in order to get the same answers. Because who knows? Do you think there's any math classes out there where instructors are just making up random formulas and the students would probably plug them in? I don't think that's actually happening, but I think sometimes as a student it's good to know where these formulas and shortcuts come from, that they don't just sort of magically appear. Okay, so anyways, that's an introduction to what we're going to be covering in Chapter 4, and like I said, we're covering 2 sections this week. The first one, the main focus, is this power rule and a couple of other rules. And then the 2 rules that are covered in the next section, section 4.2, are the product rule and the quotient rule.